Hello, Summer Institute students. Sorry I couldn't be in class today. I'm going to present here some new content. This material will not be on the final quiz that we'll be taking on Thursday, but it saves us a little bit of time. This is stuff I would have been going over after the quiz on Thursday, and since I'm missing all of Wednesday, this will get us back on track. So, we're going to take some notes on some new content. There's also going to be a worksheet. You're going to be filling in some notes on that and doing some practice problems. So please open up your notes. You can pause the video here if you don't have your notes handy just yet, and then come back in when you're ready. Okay, so the content topic here is work and energy, and you probably have some familiarity with these topics from previous science courses. And so in physics, we define work in a very physical sense. Here's our starting definition. A force does work. We'll use capital W as our symbol for work. A force does work on an object when the force somehow points with or against the object's displacement. And please write this down in your notes so you have the definitions ready to go. Feel free to pause the video while you do so. And so again, you see it's a very physical sort of thing. An object has to have a force doing work on it, and the object has to be moving in some way. Another way to tell work is done is when work is done on an object, its energy changes. We'll define energy soon, but here's another way to tell work is done. If the object's energy is changing, that's how you know work is being done on the object. Now, neither of these really defines work. They just tell you how you know work is being done. So here's our actual definition. Work is an exchange of energy. And again, we'll use the symbol capital W for work. We've used lowercase w before for weight, although we didn't really use it very much. Usually we immediately substitute with mg, but it is a capital W for work. So you don't have to copy this down. I just want you to watch this, and if you want to copy it down, that's fine. But here is a picture of a single object in three different situations. It's always the same object, and the object is always moving to the right, but a force is being applied in different ways, and we're going to see the effects of it in terms of how much work that force is doing. So in the first situation, you see the object is moving to the right, and the force is also to the right, so you might say that the force points in the same direction as the motion. In the second situation, the object is moving to the right, but the force is to the left, so you might say the force points opposite to motion. Maybe this is a friction force opposing the motion. In the third situation, the object is moving to the right, but the force is pointing up, so we'll say the force points perpendicular to the motion. In fact, you might guess maybe there's a normal force. As the object moves to the right, there's the support force on the surface. Let's see the effects of this. So in the first situation, if the object is moving to the right and the force is to the right, well, if you imagine if it's already moving to the right and you give it a shove to the right, well, what's going to happen? You're sort of helping it out, so the speed's going to increase. In the second situation, it's moving to the right, but the force to the left, what's going to happen? Well, clearly, the speed will decrease. Maybe, again, that's the friction force impeding the motion. Or maybe it's a shopping cart that's gotten away from you and you apply a force back to slow it down. In the third situation, you see the force is pointing up. Well, if in the first situation, when they point the same way, the speed increases. And the second situation, it points opposite, the speed decreases. What happens here? Hopefully you recognize that as long as that force is not enough to actually lift it off the surface, it will have no effect on the speed. Or going back to the idea we've seen before, this force in the vertical dimension should have no effect on its sideways or horizontal motion. Motion in one dimension is independent from motion in other dimensions. Now let's talk about this in terms of energy. While we haven't defined energy, you probably already have a good sense of what energy means. So in the first situation, the speed increases, well, that means the energy increases. In the second situation, if speed decreases, energy decreases. In the third situation, if there's no effect on the speed, that means that there's no change in the energy. So how does this relate to work? Well, just before in your notes, you've written that work is an exchange of energy. And so in the first situation, if energy increases, we say that positive work is being done. In other words, energy is being added into the system. In the second situation, if energy is decreasing, we call that negative work. Energy is being taken away from the system. So consider what the third situation would be, and feel free to pause the video to try to figure out what that would mean in terms of the work. So the first situation, it's positive work if energy is increasing, and here negative work is being done decreasing the energy. Here, if there's no change in energy, we call that zero work. There's no change in the energy. Zero work is being done. So the force is there, it's just not doing anything in terms of the energy. It doesn't have any contribution to the change in energy. Now we could also then take this to the idea of the angle between the two. So here the angle between this force and the displacement, well, they're both pointing to the right. We call that a 0 degree angle. In the second situation, it's moving to the right but force is to the left, so that's, of course, an angle of 180 degrees. And the third situation, what angle is that? Well, clearly it's 90 degrees. And so it seems that there's some sort of trigonometric dependence. And so I want you to try to figure out what trigonometric function would follow this pattern. That if you plug in 0 degrees, you get a positive number. 180 degrees gets a negative number, and 90 degrees gets the number 0. You may already know what trig function that is, but if not, pause the video, play around with your calculator, take out your calculator, play around with it, and try putting these angles in to see what trigonometric function fits the bill. So hopefully you figured out is the cosine function. That cosine of 0 gives positive 1, cosine of 180 gives negative 1, and cosine of 90 gives 0. So we're going to put this all together into the equation for work. Here's our definition for work. Here's going to be our equation for work. That involves the force and the displacement, and now we see it's also the cosine of the angle between the force and the displacement. This puts together all of our definitions of work as well as this idea here on the table. For the units for work, it comes directly from the equation. Force is measured in newtons, displacement is measured in meters, and when you take the cosine of an angle, it's a unitless number, so it's newtons times meters. We do rename the Newton meter as a joule, after Mr. Joule. And so it's okay if you didn't write down this whole chart here, but I do want you to write down this equation in your notes, box it in as a new equation, write down the units so you have this to work with. In the next video, we're going to go into energy, the definitions of energy, and the different types of energy.